So we're going to be looking at alternating series test and absolute versus conditional convergence. So this whole time we've been talking about, does it either converge or diverge? But now with alternating series, we have two possibilities with converging. It either will converge absolutely or it will converge conditionally. And we'll talk about how that works out. Okay, so go ahead and get your notes ready and we'll get started with that in just a moment. So our objective and our task today are going to be two things. So today we're going to be using the alternating series test to determine convergence and divergence of alternating infinite series. And then we're going to determine whether series converge conditionally or absolutely. And this last one we can actually use on more than just alternating series. And we'll talk kind of about that when we get to that point. But it definitely applies to our alternating series. All right, so first off, what is an alternating series? Well, we've talked about them before where we have that alternating kind of part of the series where we have the -1 to the n power. That is what creates that alternating series. It's when we have the terms swapping back and forth between positive and negative, we get this alternating series. Hence the word alternating back and forth. So we have really three ways that you will probably see the way an alternating series could be written. Could be in the first one where it's just -1 to the n power. Right? That's that alternating component. Or it could be -1 to the n plus 1 or -1 to the n minus 1. That would do the same thing. The first one would start with positives. It would go positive, negative, positive, negative, positive, negative in that order. Whereas the second ones, because it's plus 1, would go negative, positive, negative, positive, negative. So that's just the difference between the two, is whether or not you're starting with a positive, starting with a negative. But then from that point forward, it's going to be just alternating back and forth. And then our third one, which might be thrown at you every now and then, is cosine of n times pi, or pi n. And that is your alternating component. I want you to kind of think about that. Why would that be an alternating component?
Cosine's either 0 or -1.
Mm-hmm. Yeah, so it kind of just bounces back and forth between our 0 radians and pi radians, right? Kind of just bounces back and forth between that. And what are the values of cosine when I'm here at 0 radians or here at pi radians? So it will go 1 and then -1, and then over at 2 pi it's back at 1, and then 3 pi it's at -1. And then if I'm at 4 pi, I'm back at +1. So it does the same thing as number 1. So number 3 is pretty much the same thing as number 1, just written in a confusing, tricky way, right? So they could, right? They could throw that in there. They could do sine, and it would be n times pi over 2, right? Except on that one, I think it would probably... That one would have to be written in a different way. It'd have to, because you'd have to end up with pi over 2 and 3 pi over 2 and swapping back and forth. So I'd have to think about how that one would be written. But cosine of pi n would definitely be a very easy one to have that alternating back and forth between 1 and -1. All right, so that's alternating series. We've seen them. We've seen that alternating component. So let's talk about our alternating series test. All right, so I'll give you some time to write that down, and we'll talk about it. Okay, so I'm going to go ahead and just start going over this. So it says let a sub n be greater than 0. So we have the a sub n is a sequence where all the terms are positive. But then we throw that positive a sub n into this alternating series, and so we have that alternating component with the -1 to the n, or to the n plus 1. Again, it doesn't matter which one it is. So the a sub n, this a sub n that we're looking at here is really the sequence without the alternating component. Okay, so if you want to kind of make a note of that, a sub n is the sequence without the -1 to the n power, that alternating component. Okay? So our alternating series will converge if the following two conditions are met. The limit of a sub n is, as n goes to infinity, is equal to 0, so it's converging on the limit to 0. Or it's approaching 0 with the limit, however you want to think about it. And then our second condition is that our next term, so a sub n plus 1, the next term has to be smaller or equal to the previous term, okay, for all n. So what I'm saying down here, this is a note. I thought I'd just go ahead and throw it in for you guys as well. The non-increasing is being very technical, that it is decreasing, but there are times that the two terms could be equal. Okay, so it could be like, 1/2 and then 1/2, but then the next one is smaller at 1/3 or something like that, right? Yes.
It's not like eventual.
As far as I understand, it has to be for the full thing, yeah. So any term that you get, it needs to be smaller than the previous term, yeah. Smaller or equal to. So really, that's why it's less than or equal to. That's where the non-increasing is talking about, is that it needs to be either smaller, or it could be equal to, but it needs to either be equal or smaller than the previous one, okay? And so again, we'll be able to set up kind of an inequality and do some cross multiplication and look at things and see if we get that true statement, right? Okay. Now, if any of these conditions are not met, then our series are going to diverge, okay? And it could be that condition 1 is met, but 2 is not. Or it could be that 2 is met, but 1 is not. And in either case, or it could be that they both don't get met. If in any of those possibilities, this series is going to diverge. To converge, both have to be met. Both have to be true. Okay? So that is important. So both conditions have to be met for convergence. If any of them are not true, then the series diverges. Okay? All right, so let's go ahead and look at a problem then. Do we have all that down? Are we good with that? Okay, so let's go ahead and look at our first problem. So this is going to be our series. We're going to determine the convergence or divergence of that given series. All right, so to determine convergence or divergence, we have our different conditions. So first, we're going to be looking at the limit as n goes to infinity of a sub n. That will need to be equal to 0. We need to see, is that true? Okay. And then our second condition is that the next term has to be smaller, so it has to be decreasing. Really, you could just think about it as decreasing. The book says it's decreasing. It was just, where I got this from originally. They were being ultra specific with that. But a sub n plus 1, the next term has to be smaller than or equal to the previous term. We want to see, is that true as well? So first off, we identify our a sub n. What is our a sub n for this problem? 1 over n. Okay, well then, what is a sub n plus 1? Just 1 over n plus 1. So wherever you see an n, you're going to put an n plus 1 instead, right? That's how we get the a sub n plus 1. All right, first off, let's check our limit. So limit as n goes to infinity of 1 over n. Is that equal to 0? Yes or no? Yes, it is. We know that. That is true. So we're good there. All right, let's go ahead and look at that inequality then. So I'm going to take 1 over n plus 1. Is that less than or equal to 1 over n? Just looking at that, is that going to be true? We can logically look at that and say, yes, that's true, but we can also do our cross multiplication and check our inequalities. So it'd be n is less than or equal to n plus 1. If I subtract my n's, I get 0 is less than or equal to 1. Is that a true statement? Yes, it is. That is true. Are both conditions met? So since both conditions are met, we can conclude that our series does what? It converges. Now, it's going to be actually very rare that the AP test is going to ask whether or not an alternating series just converges or diverges. It's actually going to be that they're going to be asking, does this converge conditionally, absolutely, or diverge? And so we'll be going back to this problem later on when we get to that point. But just know that this might not be the last step. You might have to look and say, okay, it converges, but does it converge absolutely or conditionally? And we'll look at that in just a little bit. But I want to do one more of these before we do that. But before I do, any questions on this? Some people still getting it down. Good, Matthew? All right. All right, I want you to go ahead and try this one. Determine convergence or divergence of this series. All right, so let's go ahead and talk about this. What is our a sub n that we're looking at? What would be a sub n plus 1? N plus 2, good. All right, now we have our two conditions. Our first one is that the limit as n goes to infinity of a sub n needs to be equal to 0. That's what we want to know. However, what do we notice? It equals 1. Does it equal 0? So I can actually stop there, because since that condition is not met, I don't even need to worry about the second one. This diverges. It actually turns out that the second one is true. If you actually were to do it, the second condition is met. But because the first condition is not met, then we can stop and just say, hey, the series diverges. So this is not met or not true, however you want to think about it. So therefore, our given series diverges. So I'm just going to put down here, so this is my first condition. Second condition, a sub n plus 1 is less than or equal to a sub n. We do not need to check since condition number 1 failed. There we go. All right, so any questions? So that's your alternating series test. You just need to check those two conditions and see, do they get met, yes or no? And that will determine convergence or divergence. All right, let's go ahead and talk about that whole, what do we mean by converging absolutely or converging conditionally? So those are the different types. Alternating series are a little unusual in that they exhibit three different behaviors. They can diverge, they can converge, they can conditionally converge, or they can absolutely converge. Okay? And this will hold true not just for our alternating series that go back and forth like positive, negative, but it could be for any type of series that has both positive and negative values. So it could go like negative, negative, positive, positive, negative, negative, positive, positive. Though we don't technically call that an alternating series, the whole idea of converging conditionally or absolutely can still hold true for those as well. Okay? Well, I think I have one or two that do that we'll look at if we get through all of those that I have here. Okay, so to kind of get the idea, I want you to consider these two series. So we have these two series, one of which, the first one is our harmonic series, right? What do we know about series number one, about converging or diverging? That diverges by the p series, right? Okay, p is equal to 1, it diverges. But what did we just find out about this one? This is the first example we did. What did we just find out? That one converges. And that was by the alternating series test. What is the only difference between those two series? The alternator, that alternating component. So just by throwing an alternating component, making the values bounce back and forth between positive and negative, causes the series to change from divergent to convergent. This, and we'll have it out formally, but because of this condition, we would then say that, write this over here, we would then say that second series with the alternating component, it converges, but we would have to say that it converges conditionally. Okay? Conditionally. There we go. So it's when our series without the alternating component diverges, but with the alternating component converges, that is when we have conditional convergence. So just thinking about that, then what would make a series converge absolutely? If both are convergent, right? With and without the alternating component. If both converge, then that's an absolute convergence, right? And we have that formally written here, okay? Definitions of absolute and conditional convergence. So the sum of a sub n is absolutely convergent if its absolute value, so without the alternating component, if that converges, then the other one is absolute convergence, okay? And then if a sub n is conditionally convergent, if a sub n converges, but without the alternating component, it diverges, just like we saw with the harmonic series.
Should they give us one that would be conditionally convergent, but they don't give it to us as the alternating term, it would diverge like the harmonic series, like you could just give us the harmonic series without the alternating term.
Then you just say it diverges.
Asking us to say that it's conditionally convergent.
No, this will only be if you are given like an alternating series or a series that has both positive and negative values. Yeah. So I'm going to make this kind of T-chart to kind of show that. So if we have a series, an alternating series, so it has that alternating component on it, right? That is either going to converge or diverge, right? Based on the alternating series test. But then, if it converges, we can then go further and say, well, is it conditional? Or is it absolute? But again, this is only with these alternating series that has both positive and negative values. All the rest of the series that we've looked at that are not alternating are just going to be as normal, either converging or diverging. Okay? I'll let you guys get that down then. I'm going to go ahead and just write this on the side, remember. A sum with the absolute value is without the alternating component. Okay, so when they're talking about the absolute value, they're talking about it without the alternating component. Okay? Or sticking an absolute value. Like if we had that sine, or rather cosine of pi n, right? We could say that's what's causing the alternating. You could throw absolute value bars around and say we're just going to make that positive regardless, and then look at the series. Okay? Okay. Any questions? All right, so let's go ahead and look at one. This one here. Does the following series converge absolutely, conditionally, or does it diverge? Since this is an alternating series, I would recommend that you first look at this with the alternating series test. Determine, does this converge or diverge? Then, once you know if it converges, then look and see, well, is that convergence absolute or conditional? But that's the way I would go about it, kind of like, again, with that T-chart. First do, is it convergent or divergent? Then once we have determined convergence, then we'll go on and say, is it conditional or absolute? So let's go ahead and look at this. We have our two conditions. So what is a sub n that we're going to be looking at? N to the 1/3 power, or whatever, or we can just leave it as square root of n, however you want to think it, or cube root of n, cube root of n. So then remember we're doing the alternating series test, so then what is a of n plus 1? Cube root, 1 over the cube root of n plus 1, or you could just do the n plus 1 to the negative 1/3, however you want to think about it. All right, let's go ahead and look at our first condition. We have the limit. Is the limit as n goes to infinity of a sub n, is that equal to 0? That's what we want to know. And I think it is, right? We have 1 over the cube root of n. Yep, that should be equal to 0. What was that? It keeps getting, even though it's a cube root, the cube root will be getting bigger, because if you think we have the cube root of 1 is 1, cube root of 8 is 2, cube root of 27 is 3, cube root of 64 is 4, and it just keeps it. It will be getting bigger slower than other things, but it will still be getting bigger. All right, so that's good. Let's go ahead and look at our second condition, and that is that a sub n plus 1 has to be less than or equal to a sub n. Well, no, is that true? So 1 over the cube root of n plus 1, is that less than or equal to 1 over the cube root of n? Should be able to look at that and say, yeah, that's true, but we can go ahead and do our cross multiplication. So that will become the cube root of n, is that less than or equal to the cube root of n plus 1? What's wrong? Oh, okay. So what can I do here to continue to get to my true statement? Or see if I have a true statement. I can cube it, right? So that would just give me n is less than or equal to n plus 1, which leads to 0 is less than or equal to 1. Is that true? So is this convergent? All right. So this converges. But now what do we need to check?
Absolute value.
We need to look and check for absolute or conditional convergence. So this converges. So let's go ahead and look at the series without the alternator. So n equals 1 to infinity, take out the alternator, and I have this. What kind of series is that? P series. What is our P? 1/3. So is this one without the alternator, is it convergent or divergent? P equal to 1/3 is less than or equal to 1, so that diverges. So then what is our final conclusion? We can then say, therefore, again, our original one within that is conditionally convergent. That is the final answer. Okay? So you have to first determine convergence or divergence of the original series. Once you've established that, if it diverges, you kind of just end there, right? Just say, hey, it's divergent, done, we go on. If it converges like this one, then you have to step back and say, okay, well, it was an alternating series. So now I need to determine what type of convergence. So you look at this series without the alternator, determine if that one converges or diverges, and we saw it diverged. Since it diverged, then the original convergence that we had is conditional. All right? Any questions? Let's see, we have enough time, I think, for another one, so I want you guys to look at this one. This one actually turns out to be a fairly short problem because we kind of end on the first condition here. Looking at the limit as n goes to infinity, what did we notice? So yeah, we have the limit as n goes to infinity of n factorial over 2n. Which one of those grows faster? So therefore that is going to infinity. So that failed. So therefore we can conclude that our series diverges, right? So do I need to check about conditional or absolute? No, because it diverged. All right? Diverges. Because remember, it's converge absolutely, converge conditionally, or diverge, and that's the one that I have. All right, so I want to go ahead and do a couple more examples that I had in the lesson that we didn't get to. So first off, our problem number 5 here, does the following series converge absolutely, conditionally, or does it diverge? So this one is a little bit different because this is actually not an alternating series. However, the sign of n that we do have there does give us quite a number of positive and negative terms. And so this one kind of alternates in the fact that we have positive and negative terms, but it's not alternating because it doesn't follow the pattern of like positive, negative, and so forth. So we can actually look at this and determine convergence with converging absolutely, conditionally, or diverging. Well, remember what we said back in our statement here, that if we look at the absolute value of this series that we are given, and if that converges, then we don't really need to do anything else. We can just assume that one that we were originally given also converges, and it converges absolutely. It's really if we look at the absolute value and it diverges, we want to check the other one to see if we have convergence as well. So It's kind of the thought on this one anyways. And so we want to go ahead and consider, so this is not an alternating series. So we want to make sure we pay attention to that. So we can't use the alternating series test. But what we can do is go ahead and maybe look at, well, what happens at the absolute value of that series that we have. So we're going to go ahead and look at that. So n equals 1 to 8. And we're going to take the absolute value of sine of n over n squared. Now if we think about that, the only thing that gives us negatives is that sine function. N squared, that is always going to be positive no matter what. So we can actually take off the absolute value from the n squared and just think about this as this function here, sine of n over n squared. So we want to know what is the convergence of this series. Well, to do so we can go ahead and look at a comparison test, direct comparison. And the one that I'm going to compare it to, hopefully that makes sense, is just the 1 over n squared. Because that, we know what that is, 1 over n squared. That is a p series where p is equal to 2, which is greater than 1. So this converges. So again, remember what the direct comparison is, that if this converges, then we're hoping that that is greater, or at least that this is greater than that one, so that we have this larger function pushing down on the smaller function. Again, visually kind of thinking about, we have the one that's converging, that's larger, we want it to be pushing down on that smaller function. So we're hoping that so what we want is that the absolute value of sine of n over n squared is going to be less than or equal to 1 over n squared. Well, I could do some cross multiplying and different things, but something that we could actually look at, we can actually say, yes, this is true, because if we think about the absolute value of sine, well, the graph of sine itself, just sine of x, bounces back and forth between 1 and negative 1, right? Just bounces back and forth. So if I take the absolute value, remember we're looking at absolute value is the distance to 0. What is that distance to 0 regardless of positive or negative? And that distance to 0 is going to be less than or equal to 1. And so this is true because absolute value of sine of n is less than or equal to 1. And the bottom is the same, so really we're establishing that the top is true, and it is. So we know that's true, that converges. So we can say that this, or rather the absolute value of sine of n over n squared, that converges, which leads us to the conclusion that our original one converges absolutely. Okay? And so that's kind of how that one works. All right, so this is the last one that I have here. So we'll go ahead and look at this one. All right, so this one here kind of works very similar to the last problem. So this is, again, this is not an alternating series. And we see that because in here we have positive and negative values, but it goes negative, negative, positive, positive, negative, negative, and so forth. So it doesn't follow that negative, positive alternating. But we can look at the absolute value of that sequence. Okay, so we're going to look at the absolute value of a sub n. So if we do that, we see that the absolute value of all of this crazy stuff really results in that this up here, this top part is what is causing the positive and negatives. And so if we absolute value that, then all that negative just goes away, and we are left with just the function, or the series rather, 1 over 3 to the n. But this is a geometric series with r equal to 1/3. So this converges, and since the absolute value of the series converges, we can conclude, therefore, our original series with all that crazy -1 to the n times n plus 1 divided by 2 power divided by 3n, we can say that this converges absolutely. All right. So that concludes those videos. Hopefully they were helpful, and we'll talk to each other later. Take care.